In this lecture, we discuss about Eigen values of L square and Lz. Here, firstly, we find Eigen value of L square. So we write the Eigen value equation for L square. The equation is L square y Lm function of theta phi equal to lambda h cross square y Lm theta phi, where y Lm theta phi is a spherical harmonic function. Once L square operate on the function y, then it reproduces the same function multiplied by constant term. That constant term is lambda h cross square. That equation is known as Eigen value equation for L square, and it is the equation number 1. In that equation, lambda h cross square we write in terms of L into L plus 1 h cross square, and it gives the Eigen value of L square. Nextly, we put the value of L square. As you know, L square in spherical polar coordinate system, the value is minus h cross square into bracket 1 upon sine theta dabba theta into bracket sine theta dabba theta plus 1 upon sine square theta into dabba square by dabba phi square outside bracket y function of theta phi equal to lambda h cross square y theta phi. Here h cross square is common on both sides, therefore it gets cancelled. Minus sign we take on the other side, it is to be minus lambda y, and we take on one side. The equation becomes 1 upon sine theta dabba theta into bracket sine theta dabba y by dabba theta plus 1 upon sine square theta into dabba square y by dabba phi square plus lambda y equal to 0. Say this is the equation number 2. Now we solve the equation 2 by using separation of variable method. That means we put the value y equal to two independent terms, y theta phi equal to capital theta, it is function of theta, and capital phi is function of phi. Now once we separate into separation of variable method, y separate into theta and here the phi. Equation 2 we rewrite by putting the value of y as a theta into capital phi. In the first term, if we differentiate y term with respect to theta, phi is constant, we take the outside. But for the second term, differentiation of y with respect to phi, it is the twice differentiation. Again, theta is outside, differentiate only the term phi, and last term y lambda, that we write lambda into theta into phi. Therefore, the equation 2 becomes phi of phi by sine theta into dabba theta into bracket sine theta into dabba theta by dabba theta plus theta by sine square theta into dabba square phi by dabba phi square plus lambda theta phi equal to 0. Now we solve this equation such that we get the two independent terms. For that purpose, we multiplied by sine square theta by theta phi to this equation. The equation we simplify such that if we multiply sine square theta phi to the first term, then phi is the numerator term, denominator is phi, it gets cancelled. Only the remaining term is sine square theta by theta into 1 upon sine theta into dabba theta into bracket sine theta dabba theta by dabba theta. This term is as it is. Second term here, theta divided by sine square theta into sine square theta by theta phi. Therefore, this theta is the numerator and denominator, it get cancelled. Sine square theta also get cancelled. and we write only 1 upon phi into dabba square phi by dabba phi square. Third term, lambda theta phi multiplied by sine square theta theta phi. Theta phi numerator and denominator it get cancelled. Only remaining term is lambda sine square theta. Now we arrange after multiplying that term, we get the equation sine square theta by theta. We take the outside for first and third term into bracket 1 upon sine theta into dabba theta into bracket sine theta into dabba theta by dabba theta plus lambda theta. This is the bracketed term equal to on the other side. Second term we take on the other side minus 1 upon phi into dabba square phi by dabba phi square. Here that equation shows the one side of the equation only depends on theta while other side only depends on phi. Therefore, the two independent variables must be, each side must be same and equal to some constant. Hence, we write which is that constant. Each side must be equal to some constant m square. Since theta is one of the independent term, phi is also another independent term. Two independent terms must be equal. Therefore, each side must be equal to constant m square. Hence, we write the two equations separately. Minus 1 upon phi dabba 2 phi by dabba phi square equal to m square, and second term sine square theta by theta into bracket 1 upon sine theta into dabba theta inside the bracket sine theta into dabba theta by dabba theta plus lambda theta equal to m square. We say this is the next equation number 6. Now we simplify the first term minus 1 upon pi into dabba square pi by dabba pi square equal to m square. Now this minus sign we take on the other side. We get the equation dabba 2 pi by dabba pi square equal to minus m square pi. Therefore, the again equation becomes dabba square pi by dabba phi square equal to minus m square phi. This minus take on one side and this equation we take on the other side becomes equal to 0. This is the second order differential equation. Solve the equation and we get the solution phi of phi equal to c into e raised to I m phi. Here c is the constant of the integration that we find here. That c how we find by using the normalization condition, and once we get the value c we put here, we get one of the independent term in that equation, that is phi, and that phi we express in terms of constant multiplied by exponential I m phi, and the equation 6 we use in the next case as that one side must be equal to some constant m square. We find constant c by using normalization condition. Integration 0 to 2 pi phi star phi d phi equal to 1. Hence we just say phi star, the complex conjugate of phi. Phi you know, phi is equal to c into exponential I m phi. We take its complex conjugate, it becomes c into exponential minus I m phi. Therefore, the product of phi star phi, it becomes equal to c into exponential minus I m phi into c into exponential I m phi d phi, that is equal to 1. We take the c square outside of the integration. Exponential minus term and exponential plus term becomes 1. Therefore, integration of d phi, that is equal to 2 pi, since limits are from 0 to 2 pi. Hence, we get the value of the integration phi star phi d phi equal to c square 2 pi. That value is equal to 1. Hence, c square into 2 pi equal to 1. Therefore, c is equal to 1 divided by under root 2 pi. And therefore, the phi is function of phi equal to 1 upon under root 2 pi into exponential Rm phi. And say this is the next equation number 8. Now, we solve the next term. Here, the value of m is equal to 0 or plus minus 1 or plus minus 2 or plus minus 3 as m square is positive. Then we find as L square which operate on the function y, it is function of theta phi. Then how we solve it? Initially we put the value of L square in spherical polar coordinate system. The value we write in the first case, it is to be L square y theta phi equal to minus h cross square into bracketed term. Since this is the value of L square. L square is minus h cross square into bracket 1 upon sine theta into dava of dava theta into bracket sine theta into dava of dava theta plus 1 upon sine square theta into dava square by dava phi square. Outside bracket we write y is function of theta phi. Now we solve that equation. As y we separate into two independent variables theta and phi. Therefore, the next step is equation by substituting y theta phi to this earlier equation. Equation 9 becomes minus h cross square inside the bracket. Y is into two independent terms theta phi. Therefore, differentiate y term with respect to theta and phi in the equation number 9 and we get the equation minus h cross square into bracket. Phi, capital phi is function of phi divided by sine theta into dava of dava theta into bracket sine theta dava theta by dava theta plus dava theta by sine square theta into dava square phi by dava phi square. Here we simplify this equation again. Phi term we find earlier, equation 7. From the equation 7, differentiate phi twice with respect to phi. We get the differentiation of dava square phi by dava phi square is minus m square phi of phi. And therefore, the equation we simplifying in that way by putting the value of dava square phi by dava phi square, that is minus m square theta phi of phi. Here, therefore, on the other side, L square y theta phi equal to this phi we take outside. Since both terms there is one common term phi, take firstly outside and remaining terms we write inside the bracket. 1 upon sine theta into dava of dava theta into bracket sine theta dava theta by dava theta minus m square divided by sine square theta theta. Now that value we find earlier, that why we just find what is the value of that bracket. One equation we mentioned earlier, if the two independent terms theta and phi equal to some constant equal to m square, hence we choose that equation here. From equation 6, equation you know, sine square theta by theta into bracket 1 upon sine theta into dava of dava theta sine theta into dava theta by dava theta plus lambda theta, that is equal to m square. Hence, bracketed term we find its value by using this equation. Now, how we simplify this equation? By putting the value of lambda. Since lambda value is to be in terms of orbital quantum number L into L plus 1. We know the value L, we start from 0, 1 to up to last value n minus 1, where n is the principal quantum number. Therefore, sine square theta by theta into bracket 1 upon sine theta into dab of theta into bracket sine theta into dab theta by dab theta plus L into L plus 1 theta. This side must be equal to m square. Therefore, this bracketed outside bracket term take on the other side. The equation becomes 1 upon sine theta into dab theta into bracket sine theta dab theta by dab theta minus this term on the other side. We take on one side of this equation minus m square theta by sine square theta equal to L into L plus 1 theta. Since the bracketed second term we take outside and we get this resulting term. Hence, we put the value in earlier equation. The bracketed value must be equal to minus L into L plus 1 into theta. Therefore, using this equation, equation 10 becomes earlier equation. L square y theta phi equal to minus h cross square into this bracketed term. But the bracketed term is equal to minus L into L plus 1 theta into phi. Hence, minus minus it become plus. We get the equation h cross square into theta phi, that is a function y. Hence, instead of theta phi, we write directly y theta phi. Since on the other side, we also write L square into function y theta phi. This equation 11, which represent Eigen value equation for L square, and that L square has Eigen value L into L plus 1 h cross square. Eigen value is nothing but expectation value. Hence, expectation value we write in terms of the angle bracket L square equal to L into L plus 1 h cross square. And this is one of the Eigen value for L square, where L is equal to 0, 1, 2 up to n minus 1. N is the principal quantum number. L is orbital quantum number. It takes the value 0 to n minus 1. Nextly, we find Eigen value of Lz. For that case, you must know that what is Lz in terms of spherical polar coordinate system. Since it is one of the operator, z component angular momentum operator, its value in spherical polar coordinate system is minus h cross dab of phi. Now we operate function y on both sides. The equation becomes Lz y theta phi equal to minus h cross dab y theta phi divided by dab phi. Here again, separate using separation of variable method. Y term we separate into theta phi. Equation becomes Lz theta into phi equal to minus h cross dab of phi of theta phi. Here differentiation is with respect to phi, therefore phi theta term we take outside, and equation becomes minus h cross theta into bracket into dab phi by dab phi. Dab phi by dab phi, again we simplify, but as you know, phi is equal to 1 divided by under root 2 pi into exponential Im phi. Simplify this term and rewrite differentiation of exponential Im phi with respect to phi is minus this is the term as it is, minus h cross theta into dab phi of this term. The equation becomes under root 1 upon under root 2 pi is constant. Exponential, its differentiation is Im into e raised to Im phi. Simplify this term. We write Lz. since that term we take as it is, y theta phi equal to m h cross, since I into I is I square is minus 1, therefore minus minus plus, we get m into h cross as it is, theta is as it is, and the total term 1 upon under root 2 pi exponential Im phi, that is capital phi. Therefore, mh cross into y theta phi we write directly, since theta phi is the two independent terms we write for function y. Therefore, mh cross into y theta phi we write for Lz y theta phi, where m square is positive value that we mentioned earlier. Therefore, what are the values of m? M should be equal to 0, plus minus 1, plus minus 2, and so on. This is one of the another eigenvalue equation for Lz, which operate on function y. It produces the same function y multiplied by constant term mh cross. Hence, the eigenvalue or expectation value of Lz we write in terms of angle bracket equal to mh cross, and that is the eigenvalue of Lz. Earlier we find eigenvalue of L square. That eigenvalue of L square is L into L plus 1 h cross square. Hence, remember both the values, eigenvalue of L square and Lz. Thank you.